So now we're going to talk about the architecture of how we wire up components in Galaxy before we start digging into the components themselves. And so we've seen this app object a couple times. It's been around forever, and it's been just a giant object with a bunch of properties, each a component of Galaxy. Um, It is an example of a God object. So, according to Wikipedia, a God object is an object that knows too much or does too much. It's an anti-pattern in a code spell. And not only does app know too much and do too much, but it's also used in too many places. Every interesting component in Galaxy, every controller, every web transaction has traditionally had a reference to app. And we're trying to get away from that, but here is like an example of a relatively benign use of app that is still pretty unfortunate. So we've got this data set collection manager here. It's one of the first managers that I wrote. Um, and you can see we're passing it all the managers. Generally, we pass app, and a lot of them just hold on to app. Data set collection manager. When I wrote it, I realized, this app is a problem, and we need to, pull out and be more precise about what we're using. And so I actually went through and sort of said self.model is this, self.security is this, and just pulled off what I needed from app, and then constructed my dependencies, the other things I need to get my work done right here, right? And so in order to reason about data set collections, you need to reason about histories and tags and HDAs. And so we've got these other dependencies that we are constructing here. Python 3 came along, and it improved the situation with universe application ever so slightly. At least now we have types for what is on app, which is giving some structure to this God object, right? Like at least we can reason about it. At least maybe there's some IDE support for knowing, which of these 40 properties is available. So that's good. Something we could have done is sort of annotated dataset collection manager as consuming this universe application here. And otherwise this code is the same except for we've annotated the type. But the problem with this is that app itself, universe application itself, constructs a dataset collection manager. So now we've created this a dependency loop here in our imports, right? Like dataset collection manager is importing universe application, and universe application is importing dataset collection manager. Dependencies should form DAGs. And so to get around this, when we started typing app, we created an interface for it, called it structured app. Yeah. And that prevented that DAG, at least at the import level, and made those things a little bit cleaner. And so this is what dataset collection manager actually looked like after we typed it. This is great. MyPy is providing some robust type checking here. The IDE can provide some hints, and we don't have those unfortunate imports. There's still some design problems here, though. This is not an ideal situation here. Dataset collection manager needs to know how to construct all the other managers it's using and not just the interface it's consuming. App still has this weird cyclic problem where when it's constructing itself, it needs to construct everything that it's using, everything that dataset collection manager uses before it constructs dataset collection manager. And anything that dataset collection manager is needed for needs to be constructed after dataset collection manager. This is a mess. Also, app is very big here. We've got some type hints, but app is still doing a lot of work. And we are sending dataset collection manager the whole of app, and it's not using but a small fraction of it. These design problems sort of come through when you think about unit testing this component. How do I unit test this? What parts of app are being used? How do we construct a smaller app in our unit test environment that doesn't have everything in app? And how do we stub out cleanly these dependencies like the HDA manager when we're constructing the HDA manager in our constructor? A lot of these design problems go away if instead of taking an app, we take in just what we need from app, when we take in just our dependencies. As we can see here, this code, we've made the initializer argument list a little bit longer, but we've got nice and a very nice type signature, so we know exactly what we need, and the actual body is a lot cleaner, and we no longer need to know how to construct our dependencies, right? Like the thing that's constructing the dataset collection manager is responsible for that. Um, this makes unit testing a lot more precise. The typing is a little bit stronger here. We're no longer depending on app. This is fantastic. So the problem with that approach is that constructing that object is still really brittle, right? We've got inside of the universe application now, rather than just sending self, the app, we've got to still construct all of these different things and pass them in a very particular order or know all of the arguments names. So we still have this complexity in how we're creating app. We still have this, and the constructing code still needs to know how to construct each of its dependencies. And the constructing code needs to import all of those types. The object construction is a little bit brittle. We've offloaded some of that complexity to constructing the objects. Luckily, type-based dependency injection is going to solve essentially all of that for us, that last little bit. So what is type-based dependency injection? In dependency injection, a container keeps track of singletons or recipes for how to construct objects. And in type-based dependency injection, the container, keeps track of that based on the type of object you're trying to construct. So when it goes to construct an object, the container is responsible for constructing an object. And when it goes to construct it, it's going to look for recipes for all of its dependencies and construct those recursively using the container. So, for instance, when you go to construct a dataset collection manager, the container is going to look and see, well, it takes an HDA manager. How do I construct that? And it's going to take care of all of those details based on the type automatically. Practically speaking, that brittle, ugly piece of code for the construction becomes this very nice, clean thing where we just say, container, give me a dataset collection manager type. And now we have it. This is beautiful. There's libraries for Python that do dependency injection, but not many that are type-based. And I think sort of looking through these examples, it should be hopefully clear that, the typing and the dependency injection sort of together are make each other both better. And so I think it would have been a mistake to use a variant of dependency injection that wasn't type-based, that was based on the name of the object or something. And I think as you're seeing some more mature languages that have typing for longer and have dependency injection for longer, you see, the type-based dependency injection over time is just clearly the best practice for large applications. So we found a couple options. We went with Legom, but we built out abstractions that make it very easy to switch around. So we don't import Lego many places in the code. We try to have abstractions there. It's nice. It interacts with some modern frameworks. Everything is fully based on types. It works with MyPy. It's beautiful. So let's take a little bit of a look at sort of what started this. I've sort of been pushing for dependency injection for years, but when we integrated Fast API, we got a version of dependency injection that was, I think, a lot more limited. There are some really nice features, and it's better than nothing, and it's for webby things, it's okay, but it's, the dependency injection is based on defining functions that produce values, right? So the type checking still works here, but, we don't just say we want a tags manager. We sort of say this is a function that produces a tags manager. And you can go check out Fast API's dependency injection documentation. It's okay, but it only worked at the very top layer of our application. It wouldn't be good for sort of wiring managers together. It wouldn't be good for wiring anything except for those top layer controllers. And we still haven't switched to Fast API only. So all of our Fast API controllers have legacy controllers that mimic it, right? So this is some actual code that predated the use of Legom. And you can sort of see we've got two different approaches. Here we're overusing app, of course, but then we're sort of initializing the manager directly here and via dependency injection here. What was nice about doing it our own is it's a very unified approach. It's less verbose than the Fast API approach. As you can see, we are doing dependency injection based on the type, so it's cleaner. And look at all of this like legacy controller code we were able to sort of migrate away from that just became identical to the Fast API controller code. So it's much more unified, it's much less verbose, and it works for every layer of the application. Another place that dependency injection came up recently is in our migration to Celery. We have this function annotation Galaxy task here that keeps track of a list of Celery tasks and creates an app and does this Lego magic bind to container. And what that's going to do is basically query the function that you're given and sort of if there's anything in the container that it knows how to produce, it's going to bind those things to the function, which is, what does that mean? That means, like, for instance, when I do Galaxy task on purge HDA, it's going to make it so that when I call purge the HDA manager is coming from the application, it's coming from Lego, it's coming from our container, right? So that's great. Rolling our own dependency injection based on Lego, we're able to get it to use in all of these applications in ways that the Fast API dependency injection, as good as it is, just aren't really applicable. And Lego being lightweight made it very easy to do all of that and sort of use it in different contexts like that. One thing when we were building tasks, though, is we noticed that having the big structured application was good, but we want smaller variants of the app, and so we have other interfaces now for just smaller pieces of the app, so that the processes that respond to smaller individual tasks don't need to construct all of the dependencies, don't need to initialize everything that's needed for like the web application process, right? We can just get away with smaller pieces. And so all of this is very nice and structured now that we've got types. So that's how you wire together applications. Here's some tips for designing new Galaxy backend components, or even migrating existing ones. So consume only the related components you need. Avoid app whenever possible. Annotate the inputs to your component with Python types. Use interfaces to shield consumers from implementation details. And then rely on Galaxy's dependency injection to construct the component and provide it to its consumers. Sort of modern approaches to sort of wiring up dependencies. The slides here for the client aren't as fully developed, but similar thoughts and ideas are sort of instructing modern ES6 applications, modern Java applications, etc. All right, thanks.